Right. Now let's discuss furnace sequence of operation. Furnace of sequence of operation is really important because pretty much um, every kind of gas equipment is going to have a very, very similar sequence of operation if it has some kind of a douche draft or power vent motor. You might be adding an extra pressure switch if it's multiple stages. The pressure switch may go to a separate location, or you may have multiple pressure switches if it has a direct vent terminal, so it's going to be measuring positive and negative pressure on the vent. But other than that, anything with a hot surface igniter that has some kind of fan in it is going to have a very, very similar sequence of operation, whether you're talking about other furnaces, water heaters, anything like that. Even some fireplaces can be pretty similar, although generally those are direct spark ignition. Um, High efficiency boilers will be pretty similar in their operation. So it's important to get this basic set sequence of operation down, because once you have this, you've got the foundation for every other sequence of operation on gas equipment. So, digging right in, same preconditions of operation for the last few we've talked about. High voltage has to be good, low voltage has to be good, fuses have to be good, and the auxiliary safeties have to be good. Power and control wires have to be in good condition and properly terminated so that everything can operate. So, power is sent from R to W on the thermostat. Power goes to the W terminal on the integrated furnace controller or the circuit board. The integrated furnace controller verifies the limit and rollout switches are closed. If the limit and rollout switches are not closed, then nothing will operate. 24 volts travels through any flame rollout or limit switches. Generally, you'll have one limit switch and you'll have up to 3 flame rollout switches on a typical single stage gas furnace if it's able to be mounted in multiple positions, which most of them are. If it is not, then you may only have one of each. You may only have a couple flame rollouts. It all depends on the model. But any flame rollout switches you have and limit switches have to be closed for anything to continue. And then power continues to the draft proving switch or your pressure switch. The integrated furnace controller is going to verify that the pressure switch circuit is open. If the pressure switch is not open before anything starts, nothing will operate. That's to make sure that if the pressure switch is stuck closed, that the furnace doesn't run thinking it has a draft when it does not. It's pretty rare you're going to run into the situation where a pressure switch is stuck closed, but it does happen. So if nothing happens when the furnace first goes to fire up, either your inducer motor is generally bad, one of your flame rollout safeties are bad, or that pressure switch is stuck in the closed position. Um, Hold on. Let me edit this text because I took some of this sequence. From a Honeywell um, roller to get some of it down so that I could fast track what we had. So I will save that. All right. So anyway, if the pressure switch circuit is open, then the furnace control will energize the inducer. After that, the pressure switch closes and the pre-purge cycle begins. If the pressure switch does not close, the sequence will not continue. Pretty much everything on this, if something goes wrong, the sequence will not continue. So after the pressure switch closes, the pre-purge cycle begins and the inducer fan motor is going to run 15 to 45 seconds to clear any residual gas from the burners if it previously tried to light. After the completion of the pre-purge, the hot surface igniter is energized for the igniter warm-up period. high voltage is sent to the hot surface igniter, the igniter should glow. Most hot surface igniters are going to be 120 volts. They could be a different voltage, so you need to verify what kind of voltage you're supposed to have if the igniter doesn't operate and it appears to be in good condition. But generally it's going to be 90 for, I believe, some train units, and then most other ones will just be 120 volts. When the igniter warm-up period expires, the gas valve is energized and the trial for ignition begins. 24 volts is sent to the main gas solenoid valve. Try this again. 24 volts is sent to the main gas solenoid on the gas valve, generally generating an audible click. You can usually hear when that main gas valve opens. You'll hear that valve open. If you don't hear that valve open, then you need to check and make sure the main gas valve is good. Gas travels through the burner manifold, and the gas should immediately ignite because that hot surface igniter is still on. After the gas valve opens and a couple seconds pass, the power will be removed from the hot surface igniter, and ignition is proven via flame sensor signals sent to the integrated furnace controller. If the flame is not verified, gas will shut off after approximately 1 to 3 seconds. It can be really quick sometimes. I've seen boilers where it's like a half a second it has to prove flame. Generally, though, you'll have at least 2 to 3 seconds, but it depends on the piece of equipment. The main gas valve will close and the ignition process will begin again after a predetermined amount of time, usually 30 to 90 seconds, if the flame is not verified. If the flame is not sensed after 3 ignition trials, the furnace will not try to light again. If the flame sensor signal is sensed, then the fan on delay starts. After 30 to 60 seconds, high voltage is sent to the blower motor. It could be that on older equipment, the blower can actually be powered by a temperature switch. So once it reaches a particular temperature, the blower comes on. But most modern controllers just gives it a time delay and kicks it on after a time delay. Furnace runs until the thermostat is satisfied. Once the thermostat is satisfied, power is removed from W. The main gas valve is de-energized. The blower motor will continue to run for 60 to 180 seconds. The blower motor is then de-energized. Often at the same time, you will have a post-purge cycle on the inducer. I didn't put that in this sequence, but the inducer will usually continue to run for 15 to 45 seconds or so after the sequence ends to purge out any gas that might be left over after the flames shut off. And that is the gist of it. So if you can memorize this cycle pretty well, and it's not as hard as it seems, if you can memorize the cycle pretty good, then you will know what's going on without even looking at the furnace board to see what the error is, because you're going to either have nothing happen at the beginning, which generally says limiter rollout switches are an issue, pressure switch is stuck closed, or the inducer motor is not working. So you can troubleshoot those things. If the inducer motor comes on, but nothing happens, the pressure switch isn't closing. If the pressure switch closes and nothing happens, then your hot surface igniter is probably an issue. If your hot surface igniter glows and nothing happens, you're probably not getting main gas. If you get a flame on and it cuts off, you're having an issue with the flame sensor, which is probably one of the most common ones. Flame sensors need to be cleaned on a semi-regular basis. So it's pretty often you'll go to no heat, and it's because the system comes on, no flame is sensed, cuts off, does that a few times, locks out. So this is the same, like I said, for a lot of power vent water heaters. The only real difference between this and two-stage equipment is you'll have a high and a low pressure switch, and it'll generally close the high pressure switch first and make sure that the high and low pressure switch both close, and then it'll switch to low on the inducer, and just the low pressure switch needs to stay closed. Um, Other than that, it's really similar. Even direct vent equipment, you usually have a draft proving switch for the negative side and a positive pressure switch on the positive side. And you still may have a couple more for one or two more for high and low switches. The direct vent water heaters typically have 3 pressure switches, but everything else in the cycle is exactly the same. So again, you get this cycle down, you're good for most gas equipment that has some kind of blower in it. So looking at the circuit diagram, we'll go through the thermostat real fast. Well, first, same set of abbreviations so that you know what everything is. Thermostat is same as it was for straight AC, so this is just a conventional thermostat. So we have auto off, fan auto on switch, cooling thermostat, heating thermostat, heat cool switch. That's all. Now, I did the best I could to try and show a pretty complete circuit diagram of a circuit board. Most furnace controllers are going to have more relays than what I show on here, and mostly it's for humidifiers and electronic air cleaners and accessories that you might put on it. But these are the critical ones. So if you buy just like that Honeywell that I had listed on there, that I think it's the 9002 or something. I don't know. We'll look up a universal hot surface igniter, universal HSI furnace control, and the Honeywell universal ones will come up, and you'll see those a lot on boilers. Boilers and pool heaters really like using that controller. Whereas most residential furnaces will have the circuit board because it has the extra accessory slots for humidifiers and stuff. But other than that, everything works the same, and they're pretty interchangeable. But I tried to show as many of the relays and switches as I could on here to give you a good idea of everything that happens in this sequence. So we have a door switch. You pretty much always have a door switch on a furnace, with a uh, furnace circuit board. You always have the door switch on that bottom section that shuts off power to everything if you've got the blower compartment open. Some trains always got to be a little different. Some of the newer trains don't have the door switch because they've got a separate door in front of the blower, so it's not necessary. But either way, most of the time you'll have a door switch there, which cuts off power to the transformer, and basically that whole lower end of the furnace if it's opened up. So door switch, transformer powers the circuit board. L1. Oh, we're missing a line here. Door switch. And this may even be L1 is probably after the door switch too, but it doesn't really matter for general understanding's sake. L1 goes to the door switch, cuts power to the transformer. L1 also goes down to the circuit board to power everything off of it because this board has to send power to a lot of different items. So again, it's loaded with 6 or 7 relays. R goes down to the transformer. You have a G terminal to go to your indoor board. You have a Y terminal that's mostly a dummy terminal, but on some furnaces, that Y terminal is necessary for it to switch between low and high speed. So if you're unsure, you probably want to land this Y wire. It's common practice for this one to be landed, but you still see people who just will, just wire nut Y straight to the outdoor unit and not bother landing on the board. And that's bad practice in general, just because if that board requires a Y signal for the fan to kick on in high speed, then that won't occur if you don't have that terminal landed. So It's mostly, I think, like ECM motors and stuff like that, where that's becoming a necessity, but it's still really good practice. Always land that Y terminal if you're installing equipment. If the existing one is working fine and it didn't need the Y terminal landed, fine, so be it. But anything you install, I would recommend landing that Y wire just to be safe, unless you want to triple check your instructions. W terminal for heat, and then your common terminal. We can see that internally, R is going to go through a fuse. There's almost always a fuse integral to this board. So obviously, if you're having no low voltage, you might want to check that fuse. Sometimes the transformer will be powered off a set of terminals from the board instead of separately. It really doesn't matter either way. One interesting note on that, while we're on it, is if the transformer is not getting power, I have seen instances in which, for some reason, just the traces on the board, the internal electrical paths on the board, are burnt out going to the transformer. That's probably indicative of something overloading the circuit going to the transformer. But it is possible that just those traces are burnt out and you can get a system running by sending power directly to the transformer instead of sending it to the transformer from the board. But keep in mind, you'll want to look for other issues that may be causing that problem. All right, other than that, going back to the whole thing, R goes through, powers the board, and goes to the logic circuit of the board, basically through all the components of the board that make up a circuit board. Okay. That is going to basically dictate the entire operation of this system. Nothing can work without this board working. Nothing will come on without this board working, because everything goes through that sequence of operation, which this board controls. G goes through the circuit and goes to a relay that's integral to the circuit board, and that will power high speed on the fan if G gets power. Again, Y is basically a dummy terminal. W does, I don't know why I didn't draw it. It doesn't really matter, I guess, though. But W basically makes this whole thing kick on, right? The heat signal is what is going to make this board start doing its thing. So obviously, there is something in the board that senses that W is on. And then C terminal comes in, and it is important because you have a lot of relay coils that need common to operate. So you can see basically C just ties them together everywhere on here. Your neutral side comes down to the board as well. And generally you'll notice there's a neutral terminal on the board and then a bunch of neutrals all stacked together. So you know the inducer motor, your fan motor, your hot surface igniter, anything that takes high voltage is going to have a neutral landed on one big block of terminals right there on the circuit board. So we have, other than that, we'll have a limit switch, at least one, a rollout switch, at least one. Those are both going to tie onto the board. Most of these connections are that big Molex connector you see on the board, generally with 12 pins on it. So that Molex connector with 12 pins is going to be what's going to have all these signals back and forth going to it. So out of that Molex connector, you'll go through the limit switches and rollout switches, come back. You'll go into the draft proving switch, out of the draft proving switch, and right back. You'll go to the relay for the gas valve and back. You'll go to the flame sensor. Flame sensor doesn't have a return signal because this signal for a flame sensor is to ground essentially, but you'll have a wire going over to the flame sensor. While we're on it, so that I don't forget to bring it up later, flame sensor, you have to have a good ground on the board. If your board isn't grounded properly, your equipment's not grounded properly, it doesn't have a good path back to ground on your main ground circuit in the whole house, the flame sensor tends to not work properly because it needs good grounding to send that milliamp signal, that microamp signal. It's such a small signal. Anything that hurts its path to ground is going to be a problem. So you have to have good grounding. Speaking of good grounding, Did I make a note? I'm surprised I didn't make a note. I could have sworn I made a note. Maybe I made it on the highlighted sheet. But anyway, you have to have L1 and neutral have to be in the correct polarity. This whole thing doesn't work if you've got L1 and neutral mixed up. So, if somebody crossed some wires and black ain't black and white ain't white, if black's not hot and white's not neutral, then this whole thing's going to not work properly. So if any of these wires are crossed up and your hot wire is actually your neutrals and your neutral is actually the signals, generally motors and stuff still work when it's crossed up, but because there's so many things that rely on this being correct, you can't have the polarity reversed on most furnace controllers. We have our hot surface igniter, our blower motor, and our inducer motor. Now, this motor looks different than the other ones, right? This doesn't look like a compressor. This doesn't look like an outdoor fan motor. Usually your inducer motor doesn't have a capacitor, right? Some of the newer ones do, but most of the time, rooftops do a lot. But most of the time on residential equipment, there's no capacitor on your inducer motor. That's because your inducer motor is generally a shaded pole motor. So we have a main winding, and we have one, generally two. I only show one on here because you can make it work with one, but usually you'll have two shaded poles if I'm remembering correctly. It's been a while since I tore one down or looked at some information on them, but you'll have shaded poles, which are basically just little windings, low resistance windings that aren't directly connected to power. But what it does is it plays with the magnetic field of the motor so that it will come on. These are extremely inefficient. So you're talking about 30-ish% efficient. Regular PSC motors are 60-ish% efficient. So these are really inefficient motors. They're just cheap. So cheap inducer motor. So there are a lot of times they're shaded pole. When we talk about motors, you'll see that if you want to, you can. If you got the right size motor, you can replace that with the PSC. If you want to add another capacitor, and that's fine. If it does have a capacitor, if it's a PSC motor on the inducer, you do not want to put in a shaded pole because it's going to draw more amperage than the original PSC. But if you want to move from a shaded pole to a PSC, that's fine. But anyway, that's just your internal diagram essentially of a shaded pole motor. And there's your fan motor. And that is basically all the things in the circuit. Now, what I did with these relays is I showed basically the relays as cubes on this one. Probably should have done it with a defrost control board too, just so that you could see all the individual relays. But instead of labeling these relays, each coil is this set of contacts. Each coil is this set of contacts, so on and so forth. I'm not 100% sure that the way that this is drawn as far as low speed and high speed is 100% accurate at how they do it, but it's one way it could be done, so it really doesn't matter. The point is that you always make sure that low speed is on, high speed is not. So we did that by having an interlocking relay where only one set of contacts can be open at any time. And the other interesting thing to note, and this is generally true of a lot of furnace circuit boards, you can see that if you follow this power, this is all normal positions for all these sets of contacts, right? So you can see that this set of contacts is normally closed going to the low speed of the fan. And that is how a lot of them are. If you first close power, like you had this thing open, you had this door open, and this door switch was open, and then you close this door switch and send power to the fan, you'll see a lot of furnaces where the fan just kicks on for a second. The reason is that all of this is normally closed, and then as the furnace circuit board powers up, it opens this relay. So the time delay needs power for a second. Once the time delay gets power, then it opens the set of contacts that power the fan motor. And then when the furnace goes through its sequence of operation, it it basically de-energizes this relay and the fan runs. That is why you'll get that relatively common complaint of the fan motor runs all the time on a furnace. Because if that time delay circuit goes south or this relay goes south, relays tend to fail in their normal positions. So if this relay gets stuck in that closed position, then this fan's going to run all the time. Simple as that. So that's why this is shown normally closed going to the fan, because that's generally how it is. And then as soon as this board gets power, it opens the power to the fan. Hot surface igniter powered by a relay, inducer motor powered by a relay, gas valve powered by a relay. And that's it. That's the majority of it. I'm looking at it. It looks like if you look right here, I have an extra line. So I'll try and delete that at some point. That line is nothing. So I don't know why it's there. Artifact of when I drew it. No big deal. You can see it's gone over here. So I must have just moved a line or something and forgot to fix it. Okay. So let's look at the control schematic highlighted so we can see what happens. So let's try and do it through the whole sequence, okay? So in operation, this door switch is going to be closed. All right, so power is going to go through the door switch. It's also going to go to the board, okay? And it's going to go to the transformer. So you can see I got the line drawn correctly on here. So we can see power going into the board. So transformer is going to be on 24 volts. We're going to have neutral going to the board. So we get power from W. The whole sequence starts. So when this sequence starts, power to the low pressure switch and rollout switch comes back. That's good. We continue. Power to the draft proving switch. We make sure it's open. Okay, it's open. Inducer motor comes on down here. This relay closes. Power sent to this relay from the board. This relay closes. This set of contacts close. Power sent to the inducer motor comes on. Once the inducer motor is on, this draft proving switch should close. That draft proving switch closes, tells the board we're okay to continue. Once we're okay to continue, this relay closes on the hot surface igniter, and this hot surface igniter comes on. Once the hot surface igniter has glowed for a set period of time, this relay will close to the gas valve. Power will go to the gas valve. Gas valve will open, allowing gas to the system. That should immediately light the gas. Once the gas is lit, the flame sensor will sense the flame signal, tell the board we're good to go. Gas stays on. After a set period of time, or until a temperature switch closes, this relay will be de-energized, which is why we're not showing power at the relay in the circuit. This relay will de-energize. This set of contacts is normally closed, sends power to whatever fan tap is selected on the blower motor. Everything runs till it's happy. And that is the sequence of operations on a furnace and most of your gas equipment. That is what's going to occur. And that's how it's going to operate. Oh, we never looked at the thermostat. All right. Thermostat. R goes through thermostat, down through heat cool switch, through your temperature, your thermostat, basically your heating thermostat to W into the board. And that's it. So, again, kind of most important part on the furnace is just trying to remember that sequence. Doing the best you can to remember that order of events, because that order of events will help you determine what's going wrong as far as the whole gas system. Because it's gas, everything has to be set up really safe so that nothing can really go wrong. And this sequence does a good job of making sure everything goes wrong. And I guess fun fact, you can do all of this with mechanical relays. You can use latching relays and things like that to basically make all of these things happen without a circuit board. And I think the youngest piece of equipment that you're going to see doing that would be from the 80s. But that's how they used to do it. It used to be all individual relays that would power this whole system. So, power would go through these switches, go through the draft proving switch, which would be on a latching relay. So it wouldn't allow that relay to close if this switch was still closed. And then it would go through the draft proving switch, hit a relay on go through the limit switches, power the inducer. Sorry, let's try this again, right? The power would go through the limit switches. The relay for the inducer motor would be interlocked with the latching relay for the draft pressure switch. If that draft pressure switch was open, it would allow power to enter the inducer motor. Then it would close this switch, which would power the relay for the hot surface igniter, which would go through up to the gas valve, power the relay for the gas valve would come on, flame sensor signal, and then if there is no flame sensor signal, then it will go back. So anyway, you can do most of this mechanical. I think the only thing that has to hit the board is the flame sensor. I don't think you can do that without a circuit board, but it's been a while since I looked at one. But it was just cool seeing the relay set up for the draft proving switch instead of having that being controlled by the logic on a board. Anyway, that's your sequence of operation. I would highly suggest you go through this one multiple times because you will use it many times in your career if you deal with gas at any capacity. Even plumbers need to know this pretty good for water heaters, like I said, your boilers and everything else. You can switch out a couple things, instead of a hot surface igniter, it could be a direct spark ignition. This is not your sequence for a pilot. That's obviously a lot simpler, but any non-pilot equipment, this is basically going to be your sequence. And there you go.